Hello, this is my talk on the impact of the adoption of the ICRU Report 90 on the air kerma calibration at ARPANSA. And I want to say a big thank you to that incredible talk before me. What a fantastic speaker. So I have no conflict of interest and nothing to disclose. I want to again acknowledge the traditional owners of the lands on which this research was performed, that is the people of the Woiwurrung language group of the Kulin Nation and the Ngunnawal people. So in this talk I'm going to talk about what the free air chambers are, why we need to perform this update, what was involved in the update, how big the changes are and the clinical impact of those changes, what it means to the clinic and how to implement these changes for both the low energy and medium energy x-rays, or the LEX and the MEX, and let you know that there is a report coming that will have all these details in there. Quick spoiler alert, these changes are not major. The air kerma calibrations change by less than 0.5%, and we quote an expanded uncertainty of 1.4% usually at least. The change to the Cobalt 60 air kerma is a bit larger, around 1%, as presented by Tracy Bailey at EPSM last year, and that means that the interpolated iridium or cesium calibrations would be larger at 0.4 or 0.7% respectively. So free air chamber primary standards, what are they? Free air chambers are the primary standard for air kerma at ARPANSA. There are two volumes to take note of. One is the irradiated volume, which is the overlap of the aperture and the collecting electrodes, and the collecting volume, which is just the region of the collecting electrodes, the volume defined by those. So the free air chamber will measure ionization events in air. The ionization charge is collected and measured as a current, and the kerma in the irradiated volume is given by that equation below. So for the free air chambers, we measure the kerma in the irradiated volume, but we need the kerma at the point of measurement, as that is the reference point for the measurement. So to get that, we have many different correction factors that we generate with Monte Carlo. So the relevant correction factors, the first one we'll look at is the Ka, so corrects for attenuation. We know that because we're wanting the kerma at the aperture, some photons that travel through the aperture won't make it to the irradiated volume or cause any dose in the irradiated volume, so we have to correct for the under response there for the attenuation. We do know that some of these attenuated photons will have a scattering event causing an electron to deposit dose in the collecting volume, so we have to be able to correct for the increase to the measurement due to this scattering event. We also know that some electrons created in the irradiated volume will scatter laterally outside of the collecting volume, so we have a correction for the electron loss. We also know that the aperture is not perfect, so we know that there will be some transmission or scatter from or through the aperture, so we have a correction for the aperture being imperfect as well. So ARPANSA maintains two primary standard free air chambers. One is the low energy LEFAC, and then there's the medium energy MEFAC. The LEFAC is about 15 centimeters long, while the MEFAC is a bit larger at 60 centimeters long. So the calibration procedure to determine what the NK of a chamber is for a certain beam, you will have the free air chamber in place. There's a monitor chamber on the left hand side, and you turn the beam on. You get the response in the free air chamber in the monitor chamber, beam off. You move the free air chamber out and the ion chamber in, and you note that the ion chamber is located at the same position as the free air chamber aperture. Again, turn the beam on, collect the response in the chamber and the monitor chamber, and then the calibration coefficient is the ratio of the detector to the monitor to detector multiplied by the Monte Carlo correction factors. So the reasons we need to perform this update. So again, it's the publication of the ICRU Report 90 in 2016 that causes these changes to be needed. The ICRU Report 90 was adopted by the CCRI, the Consultative Committee for Ionizing Radiation, in 2017, and that is the sort of metrological body for ionizing radiation. The report updates several different key data sets for ionizing radiation dosimetry. The ones that are relevant for free air chambers are the W air and G of air, both of which do not change, but they're also the renormalized photon cross-sections, which is the renormalization of the photoelectric effect, and the introduction of the KII-KW correction factor. So the KII-KW factor is actually a combination of two separate correction factors, the KII, which corrects for the initial ionization charge being measured by the free air chamber, but not accounted for in the definition of kerma in the irradiated volume, and KW, which corrects for the increase in the W air value at lower electron energies. At about 3 keV, we see the KII is about 0.98, so 2%, and the KW is about 1.015, so about 0.15%. When we combine these factors and present them as the KII-KW factor, we see that it's a smaller correction factor, and at 3 keV it's closer to 0.6%. Also necessitating a change is that in 2016, ARPANSA purchased a new medium energy X-ray system. So the calibration distance moved from 1.3 meters to 1 meter. This is expected to be small as most of the corrections are beam geometry independent, so we expect this to be a small effect. So if we have a look at what does change, we know that the W air value and the G of air value don't change. So the other values are measurement and free air chamber dependent, so it is then the correction factors that do change. So this update involves recalculating all of those correction factors, taking into account ICRU 90. So, what was done in that update? So this update was performed using the EGGS NRC program EGGS-FAC, so EGGS free air chamber. The previous model was all done in a custom beam NRC model, which was done by Jessica Lai, and the paper reference is there. And the good thing is that EGGS-FAC allows the calculation of all required factors in a single run, so it does them all together. So EGGS-FAC calculates all the previous correction factors that I introduced before, as well as 2 new correction factors that we're including. KCPE, which corrects for the fact that there isn't true charge-particle equilibrium across the irradiated volume, and the KB, which corrects for the different scattering conditions with and without the free air chamber present. So this update, what is done is for each low energy and medium energy X-ray beam, we recalculate the old correction factors, we calculate the new correction factors, and we include the KII, KW factor for each beam spectrum. So initial model validation. So both the LEFAC and the MEFAC model were validated separately. We've used the same data as the previous work, so ICRU 37 data and the SI cross-sections, and we're comparing the monoenergetic correction factors. So this was done for a range of monoenergetic values. So looking at the LEFAC, we see good agreement in these monoenergetic correction factors between 10 keV and 80 keV. Outside of that range, we trust the new values because EGGS NRC has had some improvements in the physics models and the implementation of those physics models since the previous updates were calculated, so we're pretty happy with that. Looking at the K aperture in the bottom left, there's an interesting point to note. Because EGGS-FAC calculates the correction factors at every beam, we have a higher resolution for the aperture, transmission and attenuation correction factor, and it is a lead aperture which has a KH at 88 keV. So if we have a look at this, we see there is a very sharp increase in the transmission just below 88 keV, which is part of that cause of that deviation around that energy range. But all in all, we're happy to say that the LEFAC model has been validated compared to the previous Monte Carlo values. For the MEFAC, same order of graphs, and we see very good agreement here. So again, happy to say this model is valid. So now for the updated data. So the LEFAC, we're close to the previous values, so the electron loss, the scattering and the aperture correction are all within 0.1% of the previous values, and the Ka, the attenuation correction, is also within 0.1% except for the lowest energy beams where it's closer to 0.2 or 0.3%. The KCP value is almost unity, as is the KB factor, and the KII KW factor, as expected, is a larger correction, so that's closer to 0.2 or 0.4% correction. The combined Monte Carlo statistical uncertainties on all of these are less than 0.05%. The overall change in the LEFAC, we see a mean change of about 0.3% with a maximum of minus 0.5%. For the MEFAC again, the updated values are fairly close to the previous values. For most of the therapy beams, the changes are less than 0.1%. We have the NXJ and NXK series, which are very lightly filtered beams, and we do see some scattering differences there in the order of 0.2%. Overall, we see differences of less than 0.2% for the therapy calibrations that we offer. The KCP and KB factors are again fairly small, and again it is the KII KW factor that is having a larger change. The combined Monte Carlo statistical uncertainties for each of these beams is less than 0.06% for the MEFAC, and in terms of an overall change from the old values to the new values, we see a mean difference of minus 0.2% with a maximum of minus 0.3%. We've also assessed the impact of the changing of the calibration distance on the MEFAC from 1.3 to 1 meters. So we see there's no change to the E-loss or the scattering correction factors. There is, however, a slight increase to the KAP at the higher energy, so potentially plus 0.6. We also looked at the change from ICRU 37 to ICRU 90. Again, no change in the electron loss or the scattering correction factors, but there is a small change again in the aperture transmission correction factor of minus 0.6. So conveniently, these two changes mostly cancel each other out. So in terms of the uncertainties for the calibration service we perform, the uncertainty is dominated not by the Monte Carlo correction factors, but by other factors. So the WARE value is 0.35% as per ICRU Report 90, but we have already adopted that uncertainty increase. There's also 0.2% from the standard apart from Monte Carlo correction factors, and at least 0.2% from transferring that standard from the free air chamber to the ionisation chamber. So this means the Monte Carlo contribution is quite small, and that will mean there will be little to no change in the uncertainties in the calibration service we offer. Now importantly, what does this update change in the clinic? So the approach will be a unified approach across all the calibration services the primary standards lab at ARPANSA offers, and it will be a new correction factor FQ that will apply to any calibrations done prior to the adoption of this change. There will be a separate FQ for each calibration type and beam quality we offer. This will work by multiplying the previous calibration coefficient by the FQ factor, and the planned adoption date for this to take effect is the 1st of January next year. Any calibrations performed after the adoption date will not need this correction applied because it is inherent in the calibration coefficient we provide. So to do this, you'll get your NK value from your report. So if we zoom in on this table, have a look at that beam, there's the NK for this beam. Get the FQ from the same beam from the report that we'll be publishing and multiply those, and you can see there that you have your new NK value for this beam. For brachytherapy calibrations for iridium or for cesium interpolations, you would apply the FQ to both the cobalt 60 NK and the MEX beam NK and then perform your interpolation as usual. So to summarise the important messages, we've modelled the LEFAC and the MEFAC in this new code XFAC. We have a new correction factor to update all calibrations prior to the adoption of this update, which will be FQ. The changes for the air kerma will be small. We'll see LEFAC of less than 0.5% and the MEFAC of less than 0.3%. The report is coming with all the data and all of these FQ factors for all the calibration services we offer, and the planned adoption date for this change will be the 1st of January next year. And a reminder that any calibrations issued after the adoption of these changes will incorporate any of these changes in the calibration value you receive. Thank you very much for listening, and I'll leave you with my final Strava art entry for the APSEED competition, my 0.43 cubic kilometre ionisation chamber in Carlton North.